says it as there's a point over here, a distance A away, and a point here from the center, a distance B away. And the whole bar has length L. All right. Derive an expression for the magnitude of the electric field at point A in terms of L, A, lambda, and physical constants as appropriate. All right, this sounds like a problem in which we're going to have to use Coulomb's law and break the bar up into a selection or a group of individual pieces of charge, which I will name dq. I'm going to need a way to identify the amount of charge based on the size of dq. So I'm going to say that dq is length dx wide. And I'm going to say that the piece of charge starts a distance x away from the edge of the rod. Are these, you guys all okay with that? All righty. First, I need to express dq in terms of dx. So I have something that is integratable based on the size of the bar. So I'm going to remind us that dq would be equal to the charge density times the length. And they gave us a charge density to use of lambda naught. So I think we can just use that as our direct replacement for dq. Any question about that? All right. So I'm going to make a couple of assumptions here. Assumption number one that I think is important is that every piece of the bar is going to contribute to an electric field that is in the same direction, and that'd be the x direction. That all makes sense? Excellent. So I want to set up something that tells me how much electric field I get from this one piece of the bar. So dEx equals dq over 4 pi epsilon naught r squared. And I'm going to say that this is, based on the picture, I'm going to say that this is in the x hat direction. It doesn't discern whether the left is the positive direction or the right is the positive direction. And it doesn't really matter. It wants just the magnitude of the electric field anyway. So I'm going to sub in something for dq, but I also have to sub in something for r. This is r. So I think if I want to point to that first piece of the bar, or that particular piece, it's going to be a plus x. Oops. X. That all good? All right, then that's it. dE equals lambda dx over 4 pi epsilon naught a plus x squared. That good so far?
Even though it says derive, you can just bring up the electric field equation like that?
Yeah. Yeah, it's the Coulomb's law equation is something that we can use anytime. So yeah, we don't have to derive the expression for the electric field from a point charge. We can accept it. Now we would not be able to accept, like the electric field for like an infinite line of charge or an infinite sheet of charge. You know, when derive is used, generally they'd expect you to derive that too, but not always. I mean, some of this stuff is somewhat accepted. Like if they make it clear that it's an infinite sheet or they make it clear it's an infinite line, you might be able to use that and jump right to it unless they specifically say to derive an expression for the electric field. But this one, we can start with Coulomb's law. Now, we're not really done. I mean, obviously we have to work out this expression, but we also have to put our boundary conditions in. So we have to put where the first piece is and where the last piece is. So if I integrate both sides to get the entire electric field contribution, my first piece will be a distance A away from point A, and my last piece would be a distance A plus L away. So I think those are my boundary conditions. Right? Identify the first point and the last point. And this should sum every point in between. Now, I don't know that you guys can do this integral. I'm not sure I can do this integral. Now let's pull out all the constants. Lambda over 4 pi epsilon naught leaves me with, looks like dx over a plus x squared. Right? This might be a tough one. So the first thing I would ask you guys is, do you know how to do u sub? I don't think u sub's going to work, but you can try it. I would treat this as, if you guys who don't know u sub, you would probably be stuck here. But we could write this as the integral of a plus x to the negative 2 dx. Now, for those of you who don't know how u substitution works, you're going to learn in calculus. It's just a matter of time. So you might have been stymied here. But I believe this will work with a u sub, where our u is a plus x. To do u sub, you find something that you will substitute in. And by the way, this might be on our integral table. I just don't think it is. So I'm going to do the u sub part of it. You start by coming up with something that you can substitute. And obviously, the traditional letter to use here is u. Then you take the derivative of u with respect to your variable, so you can sub out the dx as well. So what I'm going to do is du dx, which would be d dx of a plus x, which I'm pretty confident is just 1, right? Because I would take the derivative of x with respect to x, that just becomes 1. Now, that means du dx is 1, or du equals dx. So, the way u sub works, and I'm breaking some rules for my u sub, you'll get over it. It's going to be u to the negative 2. I'm subbing in for a plus x, and now I'm subbing in for dx, so I'm going to plug in du. If you do this in your calculus class, they'd probably have you sub in your limits too and put those limits back in. That's not how I was trained to do it, so I don't do it that way, but you can. I'm just going to show you what I would do. Now you just kind of in a box do this integral. And this is a polynomial, so I just add 1 to the exponent and divide by the new exponent, which is just negative u to the negative 1 power will be my antiderivative. Any question about that? Before I go on, I'm kind of doing this in a box, like off to the side. So I'm going to sub back in what I used for my substitution, which was a plus x. So this is negative a plus x to the negative 1 power. And now I bring all of it back together. My electric field equals the integral, equals 1 over 4 pi epsilon naught, that's lambda over 4 pi epsilon naught times negative a plus x to the negative 1 power, evaluated from a to a plus l. Now I have to put in my limits. So let's see, that'll be negative 1 over a plus L minus negative 1 over a plus A. Tell me I'm doing that okay. All right. All right, done. I don't know, can we clean this up some? I mean, I guess we could write this as 1 over 2a minus 1 over 2a plus L. And that's still going to be times lambda naught over 4 pi epsilon naught. And that's my electric field. Did I miss anything? I did? Nate, did I miss anything? No? All right. I don't know. I would argue that all of you should have been able to get to here. Okay? I would expect that level of performance from all of you. Now, whether or not you can go from there to the rest of this, I don't know. I wouldn't put it on a test yet. End of the year, sure. Right now, no. What I would do is I would probably say set up but do not complete an integral that could be used to find the electric field. And then if you needed that formula to do something else, I would provide you with the formula for what the answer looks like. This step would still only be worth 1 point on the actual exam anyways. All right. Right, but do not solve an integral expression with correct limits that could be solved to determine the electric field at B. Now, we've done that one before. So, Gabby, do you want me to do that one too? Or is this one you need to see? Sure. So, the electric field at B. I'm not going to use the same definitions I used here for all of these parts because it doesn't make sense to. The R is going to be completely different, and I'd probably want to measure X differently as well. So I think I'm going to have to reestablish how I'm going to do that. So the whole thing is still length L, and B is located at distance, is it B, I assume? Oh no, it's the same distance, A. Okay. A from the edge. All right, and it's at the middle. So there's a certain amount of symmetry by doing it at the middle, but I'm still going to have my same little part here, dq. And I'm going to set the problem up the same way. I'm going to look at a single piece of the electric field. And I think my dq is creating a small piece of electric field. This new program, I hate it. That's going to be in this direction. Something like that. I'll call that my piece of electric field. Now, this one is more complicated because it's at an angle. So as I look at the symmetrical part of this problem, I think that there's a part of the problem that I can throw away and a part of the problem that I can keep, meaning there's a component of the electric field this way. And for every dq on one side, there'll be a dq on the other side that will have the same component. And there will be a component of the electric field this way. And for every one that's on the left side, there'll be a similar one on the right side. So I'm going to call this DE in the y direction, and this is DE in the x direction. And I'm pretty sure the sum of all the DEs in the x direction equals 0. So I'm not going to worry about them at all. I'm only going to worry about the DEs in the y direction. I'm going to need some pointers here. So again, I'm going to make this distance x and make the width of my point dx. Just like we did way back in September, dq is going to equal lambda naught dx. Just trying to set up the component pieces I'm going to need. I also know that this distance is r. That's the separation distance between the charge and the location I'm interested in. So I think there's nothing but r equals the root of x squared plus a squared. I think that's all I got. So I want to assemble this integral, starting with the knowledge that dE in the y direction equals, I'm going to need something here. I need an angle, and I think this is the angle I'm going to have to use. So I'm going to make this the same angle. And dE in the y direction must be equal to dE sine theta. All right, I think I've got all the pieces together. Let's go ahead and throw this off to the side so we can go ahead and craft what dE is. So dE is going to be equal to dq over 4 pi epsilon naught times r squared. And that's just in the direction of r. we're going to have to do some substitutions and recognize that we're only interested in DE in the y direction. So in order to do DE in the y direction, dq over 4 pi epsilon naught r squared sine theta. Then dq is going to be lambda dx over 4 pi epsilon naught. R can be replaced with x squared plus a squared to the 1/2 power but squared. So just that, sine theta. I either have to get this all in terms of theta or all in terms of x. I think it's easier to get this all in terms of theta, but we need something to express theta in differently. So when I look up here, sine of theta would be a over r. So I'm going to do that. Sine of theta is a over r, which is x squared plus a squared to the 1/2 power. Wow, this is a mess. Yeah. Well, luckily we don't have to do any work with it at the end. So sub it all in, and I'll get lambda naught dx over 4 pi epsilon naught x squared plus a squared times a over x squared plus a squared to the 1/2 power. That's d e y. That's just one contribution to the electric field. So I want to add up all of the contributions to the electric field from negative L over 2 to positive L over 2, or, which I would recommend you do, put a 0 there and double it. However, you can't do this integral. Not yet. So that's why they only made you derive the integral, not do anything else with it. But I will say that it would make me happy if you knew what things you should take out, what things you should leave in there. So taking the 2, the lambda, the 4 pi epsilon naught, and leaving inside the integral a over x squared plus a squared to the 3/2. Because if you look this up on an integral table, you need a there. Promise. Okay. And because it's going to be in the antiderivative. But also, if you had done this in terms of theta, you'd get an equally nasty thing you'd have to take the integral of, but there'd be a lot of trig identities. This actually is solved with a trig identity anyways. So I am not good at it. You guys are mathletes. You should look into it. But those of you who have resources, just look it up on an integral table. Two small identical spheres, each with negative charge, negative q, are fixed in place a distance d apart from one another as shown in figure 1 in an xy coordinate system. Sphere 1 is at coordinates negative d over 2, 0. And sphere 2 is at coordinates positive d over 2, 0. Point P is located at coordinates d half plus d half, as shown. The sphere's diameters are both much less than d. So that's code for them saying that these are point masses. So to get us kind of started here, I've got point mass here, the origin, a point mass here, and we're interested in point P, which is here. This is negative Q, this is negative Q, this is D over 2, this is D over 2, and this is D over 2. All right. The dot in figure 2 represents point P. The dashed lines indicate the directions in the horizontal, vertical, and 45 degree from point P. The 8 directions are labeled in terms of their orientation, going clockwise. Great, whatever. On the dot in figure 2, draw an arrow representing the direction of the net electric force that will be exerted on a positive test charge located at P. The force must be represented by a distinct arrow starting on and pointing away from the dot. Well, I don't need that little thing to tell me that there's going to be a large force this way and a smaller force that is not 45 degrees. That's greater than 45 degrees. But those are the two forces that would act on a positive particle. And they'd be attractive forces, so they'd be towards the particle. So something like that. I would probably place this greater than 225 and less than 270 is where I would draw my arrow. Any question about that? Yep.
Why would you place it above the 225, like between the 180?
Because I'm pretty sure this force is going to be a lot smaller than this force.
Right.
It's more than twice the distance away, and that value will be squared, making it at less than a fourth of the other force. On the exam, you'll handwrite your response to free questions in a test booklet. Yay. Justify, I think I just justified. So am I good to go on? Yeah. Derive an equation for the magnitude of said force on the test charge. Alrighty. I'm going to work this one at a time, but I want to be very clear. I am probably going to have to break up one of these into its component vectors, the x direction and the y direction. Does that make sense? So one of them is fine. So let's do that one real quick. E in the y direction from, let's call this charge 1. So this is from charge 1. It's just going to be, do we have an expression to use for q? Is it positive q? Oh, positive little q. Okay. So negative q, positive q over 4 pi epsilon naught d halves squared. So in the y hat direction. All right, that's all I have to do for that one. Any problem with that?
I don't think that's where the point charge is.
Where's the point charge?
On the y-axis.
Oh, it's placed just anywhere on the y-axis from the middle. Oh. Well, all those things I just said, forget them.
Okay.
That's what I get for not paying close enough attention. You deserve a better teacher. So we're somewhere here, a distance y away. Is that, am I reading it right now? All right. Well, that makes it so much easier because there's only going to be the y component. The x component is going to cancel out. Is that all right with all you guys? All right. I get to have y in my answer, so yay. So it's charge q. I'm only going to worry about the component that's in the y direction, but I will have to do a little trig for that. So I'm going to say that the force component is this way. I'm going to deal with one of them and then double it. That okay for you guys? All right, well, the size of the force in this direction is going to be q over 4 pi epsilon naught times, I need the separation distance here, and that's going to be d over 2 squared plus y squared to the 1/2 power squared. All right, I did it all in one step. Is that all right with you guys since we did this exact same thing just a minute ago?
Yep.
All right. So, but I only want the component that is, straight towards the center. So if this is theta, I want the cosine component of theta. And I'm going to have 2 of those. And that'd be the total force. I need to express cosine of theta. So cosine of theta is going to be adjacent over hypotenuse. So let's mash all of that together. And kind of out of space here, but I'll do it nice and big. Mashing it all together. I'll have 2 little q, big Q, y, all over 4 pi epsilon naught d over 2 squared plus y squared to the 3/2 power. That's got to be the answer. It's a mess, but that's got to be the answer. Does the force go to 0 and y goes to 0? It needs to. And it looks like it does. You guys see what I'm saying? And also, when y is much greater than d over 2, it should turn our thing into a point charge. And it does. When y is much greater than d over 2, that term goes away. And we get 2qq over 4 pi epsilon naught y squared, which is kind of what I expect. If we're very far away, it won't matter how far apart the two charges are. They'll act like a point charge that has twice the charge. Right? So that's if y is much greater than d over 2. So it kind of fits what happens when y is 0, the electric field is 0, and when y is much greater than d over 2, it acts like a point charge. So I'm all good with that. That seems to work out okay. So yeah, if that charge came positive, it would change the direction of the force, and it would change the fact that you'd use sine for the components, not cosine. Alrighty. Yeah, that's fair. That's a fair question.